Hi, my name is Aryan Poddar. This is my lab report for Physics 2211. This lab investigates the motion of a falling object. I'll first state the purpose of the lab and introduce the system and its surroundings while explaining key concepts such as Newton's second law and the momentum principle. I'll then analyze the ball's motion using the tracker software and create computation models based on the data collected. One model will account only for the gravitational force while the other one will account for the drag force as well. I'll then produce graphs using the real-time data collected and the computation model and compare them. Finally, I'll answer some essential questions. The purpose of this experiment is to apply Newton's fundamental laws of motion in the real world. This lab focuses on Newton's second law and verifying its accuracy by comparing position time graphs created using the data collected in the real world and data produced using the two computation models, one accounting for the gravitational force only and the other accounting for gravity and the drag force. Newton's second law explains how forces acting on a system from its surrounding cause changes in the momentum of the system. The system in question is a paper ball. Since there's a net force acting on the paper ball, there'll be a change in its momentum and also a change in its final velocity. The net force comprises of the force of gravity, which is given by minus m into g into j hat, and the drag force, which is proportional to the velocity squared. I'll first record the motion of the paper ball falling. Then I'll import the video into tracker software and track the position of the ball at set time intervals. Next, I'll manipulate the starter code in GlowScript to create two computational models, one accounting for only the gravitational force and the other accounting for gravity and the drag force acting on the ball. Then I'll create position versus time graphs based on the data collected and for the computational models and compare the three graphs created. This is my track analysis done using the tracker software. The initial velocity of the ball is 0 meters per second. Since the ball is falling down, the motion is in the negative y direction, and the initial position is minus 0.01 meters. The curved section suggests that drag force has an effect on the ball's motion, which is directly proportional to the velocity squared. The straight section of the graph implies that the ball achieves a terminal velocity on its way down. In this experiment, I assumed air resistance, outside force, and friction to be negligible, hence creating a condition of constant net force. Time was measured once the ball started moving and stopped once it reached 0.7 meters. Next, I created a computational model only accounting for the gravitational force. A ball of mass 0.0145 was used to represent the crumpled paper ball. The initial velocity vector is set to 0, 0, 0, delta t is set to 0.001, and gravitational force is set to 9.8 meter per second square. I then use position update formula and velocity update formula to map the movement of the ball. The next computational model accounts for the gravitational force and the drag force acting on the ball. A drag constant of 0.0092 was included. This was adjusted so that the graph created using the computational model matched the one in real life. Now comparing the three graphs for observed position of the predicted models. In the beginning, the models all act relatively similarly. However, towards the end, the model with both gravity and drag is closer to the observed model. The model only considering the gravitational force seems to deviate largely for higher time intervals. Irregularities can also be seen because of shifts in center of mass and x-axis movement. Finally, answering the essential questions. What if the object was initially thrown downwards? The initial velocity of the object will not affect the terminal velocity achieved by the falling ball. This is because the ball would then experience a higher drag force, resulting in the same terminal velocity to be achieved. Comparing the two models, it is observed that the model accounting for the drag force as well as the gravitational force was much more accurate, as this resembled the conditions in real time.